Question 12 on the math subject GRE practice test. This is another question that I kind of like. We're getting into some kind of elementary number theory here. One of the things that's kind of cool about this question is you can do it really quickly if you sort of understand what's going on. So let's read through this problem and try to understand what's going on. We have these two prime numbers p and q, and what we know about them is p is less than q, and each of them is greater than 2. So p and q are odd primes. And now we're going to define this set M to be the set of all positive integers n such that n to the 5th is divisible by p cubed and 64q to the 11th. Okay, that's kind of a mouthful. If you really like the symbols, what we're saying is that M is the set of all positive integers such that n to the 5th, so the 5th power of a number in this set, is divisible by p cubed. In other words, p cubed divides n to the 5th, and 64q to the 11th divides n to the 5th. So the way you determine whether or not a number is in this set is you consider the 5th power of that number. So the numbers are given here. We got 5 of them. To figure out if these numbers are in the set, we need to know the 5th power of these numbers. What the question is asking is, what is the least integer in this set? So the way I think about that is there's really two things we're looking for. One, are these integers in the set? And then 2, of the integers in the set, which is least? So maybe we start with 1 here. We got 5 different options and we want to know which of these 5 options are in this set M. Well, again, to figure out whether something is in M, you don't look at n, you look at n to the 5th power. So let's figure out what the 5th power of each of these are. For A here, I would get 2 to the 5th power times p to the 5th power times q to the 5th power. For B, I would get 2 to the 10th power times p to the 15th power times q to the 5th power. If you struggle to see that, what I'm doing is I'm rewriting 4 as 2 squared. And then when I raise this product to the 5th power, I sort of distribute that 5 to each of these different factors. So I get 2 squared to the 5th power, p cubed to the 5th power, times, I guess, q to the 1st power to the 5th power. Maybe that's a little unnecessary. And then we have exponents raised up to exponents. You just multiply them. 2 times 5 gives me 10. 3 times 5 gives me 15. And 1 times 5 gives me 5. Similar logic allows me to write the 5th power of 4pq cubed as 2 to the 10th, p to the 5th, q to the 15th. And it allows me to write the 5th power of option D as 2 to the 10th, p to the 15th, q to the 15th. And then finally, recognizing that 32 is 2 to the 5th, I can write the 5th power of option E as 2 to the 5th to the 5th. In other words, 2 to the 25th. P to the 5th, q to the 10 times 5, or 50th power. So are these integers in M? Is this divisible by both p cubed and 64q to the 11th? Well, interesting thing here. This question is written in kind of a strange way. Notice that p cubed and 64q to the 11th are relatively prime. And the reason that's true is because 64 is just 2 to the 6th power. And since p and q are odd primes, p cubed and 2 to the 6th times q to the 11th, these are the prime factorizations of these two numbers, and we can tell just by looking at them that they don't have any prime factors in common. Because they're relatively prime, to be divisible by each of them individually is equivalent to saying divisible by the product of the two. What I'm saying is, rather than check to make sure that n to the 5th is divisible by this and divisible by this, we can kind of cut our work in half and make sure that n to the 5th is divisible by the product of these two. Just make sure that 2 to the 6th, p to the 3rd, q to the 11th evenly divides n to the 5th power. Depending on how comfortable you are with prime factorization, you might be able to just look at these n to the 5th and tell that what won't work for this one, won't work for this one, but it will work for these remaining 3, I believe. The reason 2 to the 6th, p cubed, q to the 11th does not divide this is I don't have enough 2's, and it looks like I don't have enough q's either. Right? If I took this number, 2 to the 5th power, p to the 5th power, q to the 5th power, and I divided it by 2 to the 6th power, p to the 3rd power, q to the 11th power, I could cancel out a lot of stuff. I'd cancel out all of these p's with 3 of the p's up here, so I'd left with p squared. I cancel out all of these q's with 5 of the q's here, so I'm left with q to the 6th power. And then I cancel out all of these 2's with 5 of these 2's, and I'd be left with the 2 here. Because this reduces to a fraction, not a whole number, this is not divisible by this. In order to be divisible by 2 to the 6th, p cubed, q to the 11th, I must have at least 6 2's in my prime factorization, at least 3 p's in my prime factorization, and at least 11 q's in my prime factorization. I can tell just visually that b is not going to satisfy the criteria either. I'm not going to have enough q's, right? I got 2 to the 10th, p to the 15th, q to the 5th. I try to divide it by 2 to the 6th, p cubed, q to the 11th. I'm able to get rid of all the 2's, that's good. I'm able to get rid of all the p's, that's good. But I'm not able to get rid of all the q's. If I reduce this fraction, I'd get what? 2 to the 4th, p to the 12th, divided by q to the 6th. Again, I'm left with the fraction. This number does not divide n to the 5th power. B is not in this set M either. Maybe I should be crossing these off or something. But C will work. Hopefully you're at the point where you can just look at it and tell. Got enough 2's, got enough p's, got enough q's. If you really want me to prove it to you, 2 to the 10th, p to the 5th, q to the 15th is evenly divisible by 2 to the 6th, p cubed, q to the 11th, because the quotient of those two numbers, 2 to the 4th, p squared, q to the 4th, is a positive integer. This number right here times 2 to the 6th, p cubed, q to the 11th is equal to 2 to the 10th, p to the 5th, q to the 15th. There's something I can multiply this by to make it equal to this number. Therefore, this number is evenly divisible by this thing right here. C is in my set. By the exact same logic, D is in my set. I have plenty of 2's, I got plenty of p's, I got plenty of q's, and E is in my set. I'm done with my first step. Are these integers in M? Yeah, 3 of them are. I don't know, C, D, and E are. Now I get to move on to step 2. Which of these 3 are the least? Just looking at C and D, we can tell that C is less than D because they both have a 4 in their prime factorization. They both got a q cubed in their prime factorization. But this one just has a p in its prime factorization, whereas this one has p cubed. So D is bigger than C. D is certainly not the least answer. What about C and E? 32 is bigger than 4. P is the same as P. Q to the 10th is bigger than Q cubed. So clearly this is bigger than this. This ain't my answer. Out of C, D, and E, C is the least. Since C, D, and E are the only ones in this set M, C must be my answer.